Hello students, welcome back. Let us go to the very last topic, the last optional topic. This time, proof by induction. By the way, here's a reminder where we are now. Proof can be separated, can be classified like this: direct proof, indirect proof. Among the indirect proof by contradiction we talked about, proof by mathematical induction. Let's talk about it now. The mathematical induction goes kind of like this. First, we have to prove the general case, either k equals to 0 or k equals to 1. If you have a statement that works for arbitrary positive real numbers, start from k equals to 1. And if it works for arbitrary non-negative real numbers, arbitrary positive integers, excuse me, did I say positive real numbers? Sorry about that. For arbitrary positive integers, then start from k equals to 1. And a statement for arbitrary non-negative integers, then start from k equals to 0, because that is the starting point. Next, we assume the conclusion is true for n-1 and proof for n. Basically, it goes like this. For k equals to 1, we prove it, okay. And because of this inductive proof over here, n-1 to n, basically what we get is k equals 1 case give me k equals to 2 case. And that gives me 3. And that gives me 4. And that gives me 5, and so on, and we'll have arbitrary n. Another way to do it is start from k equal to 0 or 1 as usual, and then instead of assuming for n-1 and proving for n, we assume for n and prove for n plus 1. It works just fine. The same idea. Get it done for k equals to 1, alright, base case. So 1 gives me 2, 2 gives me 3, 3 gives me 4, 4 gives me 5, and so on and so forth, and cover arbitrary n. Exactly the same idea. Which one do I prefer? I usually do it this way. Assume for n-1 and prove for n. But a lot of people do it the other way. Assume for n and prove for n plus 1. Among my colleagues, Ali Shakla usually do it this way. And I noted Richard Chandler also does it this way. But my way is usually n-1 to n. Okay, alright. I'm not so certain how does Noreen Khan approach. I think she also does it the other way. For n and proving n plus 1. I think she does it that way too. Well, but my way is n-1 to n, so let's do it that way, at least in my class. Let's prove this. 1 plus 2 plus 3 plus 4 plus all the way up to n is equal to n times n plus 1 over 2. How do we prove it? Let's prove it for the base case. When n equals to 1 case, if n is equal to 1, then what do we get? 1 is equal to 1 plus 1 over 2. That's true. We have 1 is equal to 2 over 2. So base case, done. Next, assume for n-1 and prove for n. So this statement here, assume for n-1. So 1 plus 2 plus 3 plus all the way up to n-1. And then here, I have to replace n in place of, I have to replace n by n-1. Okay? So it doesn't go all the way up to n. Stops at n-1, and this one we have to take appropriate adjustment. Instead of n, we plug in n-1. Or equivalently speaking, n-1 over 2. Why am I losing color? n n minus 1 over 2. Okay, all right. So from the inductive hypothesis, let's suppose this is true for n minus 1. So up to n minus 1 it works out. Let's suppose that. And then that gives me this part. All right, equality. And then we add n to both sides. So from here, looks like we don't really need this part. So from here, add n to both sides, which I highlighted in red. And on this right-hand side, let's do a bit of algebraic manipulation. This n is 2n over 2 by taking the common denominator, and take n out as factorization and manipulate. What do you get? We get precisely what we wanted, n times n plus 1 over 2. Is that what we wanted all along? Yes, indeed. That's how you do mathematical induction. First example. How about the second example here? All right, let's talk about the second example. 1 squared plus 2 squared plus 3 squared plus all the way up to n squared is equal to n plus 1 to n plus 1 over 6. Okay, let's prove that. Base case, when n equals to 1, that's not too difficult. One squared is equal to 1 plus 1, 2 times 1 plus 1 over 6. That's of course true. We get 6 over 6. This is 2, that's 3. 2 times 3 is 6, so 6 over 6. Okay, all right. Now suppose this holds true for n minus 1, which means up to here, and then replace n by n minus 1 over there, and that's what this is. And to the right-hand side, replace n by n minus 1. Let's simplify this a little bit. So in place of n here, I put n minus 1 there, so I get 2n minus 2. So let's simplify just a little bit, and this is what we get. n minus 1 times 2n minus 1 over 6. So that's the inductive hypothesis. So if I do all this addition of n minus 1, we get this. All right, and then let's go over to k equals to n case. And we add n squared to both sides of the equality. And left-hand side is now all set. 1 squared plus 2 squared plus 3 squared all the way up to n squared now. The right-hand side, some algebraic manipulation. Take common denominator and then break up the parentheses and then factor all those back again. It's not too difficult. It's just quadratic trinomial, or excuse me, cubic trinomial. We end up with n plus 1 times 2n plus 1, precisely, this one, precisely what we wanted all along. That's how we do mathematical induction. Now, in case you want to do the other way around, instead of assuming n minus 1 and then proving for n, which I usually do, some people may want n and prove for n plus 1. Yeah, a lot of people do it this way. I'm pretty sure that Richard Chandler and Ali Shakla both do it this way. Maybe Noreen Khan as well. Okay, here we go. The base case, of course, n equals 1, that's simple. And then for all the way up to n, we just assume this entire thing. So that part, oh come on, for that part, we just assume. So that part, we just assume. And then we go to n plus 1 case, so we have to add one more term here, which I'm highlighting in blue. Now the left-hand side is all set. 1 plus 2 plus 3 plus all the way up to n plus 1. The right-hand side needs some work. Taking the common denominator and factoring out n plus 1, we get what we want. N plus 1, n plus 2 over 2. Now, is this what we want? Is this what we get by replacing n by n plus 1? The answer is yes. Yes, indeed. So there goes the proof. So here, replacing n by n plus 1 came at the end. In the previous method, replacing n by n minus 1 came in before. In the end, we get precisely the same thing as before. Here, we started from the precisely the same as before, and then the final form is the replaced form. So which way is better? The same, the equivalent. I just use this one more often, n minus 1 leading up to n. If you prefer the other way around, don't bother, just stick to your favorite method. There's some further exercises, so I'm going to leave those to you. And as for strong induction, not in this course.